Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Arif Aiman, and then my friend's name is Muhammad Adam Ashur bin Muhammad Nasir. Okay, and then yeah. By the way, good morning everyone. Today, uh, my partner and I will present our project on the marketing campaign optimization problem or MCOP. At its core, at its core, MCOP is a real-world application of the famous traveling salesman problem. Imagine a marketing team from University Polytechnic Malaysia, as we know as UPTM, that needs to visit for international location city B, city C, and city D exactly once before returning home. Out exactly once before returning home. Okay, and then our goal is to find uh, the most cost-effective route possible. This is a critical challenge because as the number of cities grows, the possible routes increase exponentially, making it impossible to solve manually. To tackle this, we explore five different algorithm strategies. Okay, greedy, dynamic programming, backtracking, divide and conquer, and sorting and searching. Sorry. And yeah, okay, for part two, okay, um, part two is greedy and dynamic programming. Okay, let's start with greedy algorithm. Okay, uh, this approach is simple. At every step, you make the best immediate choice without worrying about the future. In our project, the algorithm starts at UPTM and always pick the cheapest university. Sorry, and always pick the cheapest unvisited city next. For our data, it choose city B, then city, then D, then C, before returning to UPTM for a total cost of 88. It is incredible. It is incredibly fast, running in O N two time, but there is a major catch. It doesn't always guarantee the absolute best result for more complex map. Next, we look at dynamic programming or DP. Unlike greedy, DP guarantees the optimal solution every time. It works by breaking the journey into overlapping sub-problem and using a bit mask to track visited cities. To save time, it uses memorization to store result and avoid recalculating the same path. While it is slower and use more memory than greedy, it is the most dependable method or for ensuring the lowest possible cost. But
Assalamualaikum warahmatullahi wabarakatuh. I'm Muhammad Adam Mashur Muhammad Nasir, and I gonna continue from what Mr. Arif left. We are going to move on to backtracking. So backtracking is a more thorough brute force approach that explores every possible route. However, we made it smarter by using pruning. If a path cost already exceeds our best known total, the algorithm stops and then backtrack to try a different way. While it successfully found our optimal cost of 88, its complexity means it can get very slow as you add more city. For example, how backtracking works. First, we start at UPTM. We create a path. Let's say path 1, as you can see on the slide. We start at UPTM and then to CTB and then to CTC and then to CTD and then back to UPTM. The path value is 100. Now we move on to the past two, we start from UPTM and then CTB and then CTD and then CTC and then UPTM. We found the value is 88. Then the methods turn back, start back, create a path tree. We start at UPTM and then CTC. However, the method stops. It stops calculating. It stops whatever jobs they did because the cost already exceed 88. This is where we found 88 is the optimal cost. However, if you add more cities there, I'm sure the method will be much slower. Let's move on to divide and conquer. So we implemented divide and conquer. This technique splits the cities into two halves, solves for each half, and then combines them, while it provides a very logical and organized structure. We found it isn't a natural fit and organized structure. We found it isn't a natural fit for this specific routing problem. It essentially runs like backtracking without a clear performance advantage for this type of task. Beyond just finding routes, we look at how to manage data, like student leads records. We use insertion sort to organize lists in ascending order. As you can see on the slide, the output of sorted array is 1 and then 2 and then 3 and then 5 and then 8 and lastly 9. You can see it's ascending. It's easy to code and perfect for small data sets, though it becomes inefficient for massive databases. Once the data is sorted, we can use binary search. This is a high speed search that repeatedly cuts the search range in half. It is significantly faster than checking every single name one by one, allowing UPTM marketing team to find specific priority scores or student records almost instantly. To summarize our findings, all for all for our primary routing algorithms, which is greedy, greedy algorithm, uh, dynamic programming, backtracking, and divide and conquer. These algorithms successfully identified the optimal root cause of 88 for our four city scenario. However, there is an option, which is the best one, second best, and the third best. Provenly, you can see all the algorithm proves that it can solve uh, the problems, but which is the best? The best one is dynamic programming was obviously our overall winner for their reliability and large scale use. For greedy, it was the most practical for our specific small dataset because it was the fastest. And then for backtracking and divide and conquer, serve as excellent exhaustive search but show limitation in scalability. That's all from us. Thank you. Assalamualaikum.